and welcome to another Advanced Unity 5 tutorial. Today we're going to recreate Minecraft, or a good portion of it. And to begin with, we're going to create the landscape because that really is the most important part of Minecraft. The Minecraft landscape is generated randomly, so every time you start a new environment, you get a new landscape. Creating the landscape in this manner is called procedural generation. So it's using code to create a random landscape every time. So I'm going to show you some of the techniques they actually use in creating Minecraft in this tutorial. So first of all, you need a new 3D project, which I've got here. Now you'll see in my assets that I've got a few other things. Don't worry about these. I'm going to use them to illustrate something a little later on. You should just have a completely blank project. And you'll have a light and a camera in there. So to begin with, we want to create a cube because the cube is the basic building block for the whole Minecraft landscape. Now onto this cube, we're going to put some grass. Now I found a grass texture on Google. So here we go. This is it. If I drag and drop it onto there, it'll create us a new materials folder and create that material automatically for us, which is very nice of it. And we have a basic Minecraft building block. What we're going to do with that is use it over and over and over again. So we need to create what's called a prefab. To make a prefab, you grab the cube from the hierarchy and drag it and drop it into the assets. That will create a copy of it, which becomes a template. I'm going to call this grass prefab. And so we can use that grass prefab as a template and create hundreds and thousands of these blocks that are all exactly the same. So we have a prefab and we can delete that from the hierarchy. Okay, and notice that the prefab will stay there. If you drag the prefab out into the scene, you'll get a copy of it. We don't need that. Okay. Next, we're going to create the script that will generate the landscape. So in the project, let's go create C# script. And let's call that generate landscape. Okay, and then double click on it to open it in your editor of choice. Right, so here's the script that comes as default for our generate landscape class. I'm just going to quickly replace that with my starting code, which you can pause the screen and type in yourself as we go through. So first of all, we're going to create the size of this landscape. So its width and depth will be 128 by 128. And this is the size of the ground plane, the area that it's going to take up. Next, we need to know what a block is going to be so that we can reuse that block over and over again to put it on the landscape. We next have this nested loop, for loop. So we're looping through the Z in one direction and we're looping through the X in the other direction. And each time we're setting a Y value of 0. Y will be the height of the block. We then use the X, Y, and Z values to create a new vector 3, which will be the position of the block. And then we instantiate the grass block or a grass block at our block position with a default rotation. Okay, so save that once you've typed it in. And we'll just switch back to Unity. We need to put that script into Unity. So I'm going to create an empty game object and call it landscape. And then attach that script to landscape. Okay, now if I select it, you can see in the inspector that we can set our width and depth here. I'm sticking with 128 by 128 because in this initial method that we're using, if you put too many blocks, it's just going to grind to a halt. This is probably a nice size to work with. Now you'll see that we've got the exposed variable for our grass block. And we're going to grab our grass prefab and drop it into there. Okay, now providing we don't have any typos in the code, if we press run, we should end up with a landscape. Now I can see that the camera has found it. Let's see where it is in the scene. There it is. I'm just going to zoom in a little closer. And this scene is made up of, 128 by 128 of cubes, or copies of our cube. So if we zoom in quite close, you can see that I've highlighted one of those cubes and I'm dragging it around because it's an individual game object. So they've all been created at height 0 because that's what we've programmed it to do. And you can see the clones of all of the prefabs in your hierarchy. All right, okay, so we'll stop playing that now. Let's go back to our code. So this is the code, and this is where the height of the blocks is used. Now you might want to lift the heights up because a landscape in Minecraft is not flat unless you start with a flat world. But if you want the mountains and all the different biomes and that, then you need to have some height. So what we're going to do here that you might initially want to do is to make it random. Let's start by seeing what random will give us. So we'll use the random.range function. And this takes a parameter between the lowest value and the highest value. I'm going to go between 0, which will be our lowest ground. Let's set it to, let's say 10. Now, this will probably complain if I don't make it cast to an int, so I'll just do that now. And by casting to an int, we should get nice rounded values like 1, 2, 3, 4, no point values, which will make all of the blocks pop to like one distance apart so that it will look more like a Minecraft world. Let's save that and just run it. Okay, now what we've ended up with is a little bit unfortunate because you can see that what the randomness has done. Okay, the blocks are still in their same XZ setting, but one block's height does not influence another block's height. With a landscape tends to go down and up in a sort of a wave type pattern where one block's height does kind of influence where the next block is going to be. So you can't achieve that sort of effect using pure randomness. Okay, so we need to find another method to generate our heights of the landscape, and we want to do it procedurally, so we need to be adjustable so that each time you run it you can get a different landscape. So we're going to use the algorithm, the same algorithm that is used in Minecraft for creating landscapes and is used all over the place. Once you learn about it, you'll see it everywhere. And the method is called Perlin noise. Okay, so it was created in 1983 by a mathematician or a computer scientist called Ken Perlin, and he created it for generating procedural textures in the Disney movie Tron. He actually won an Academy Award for it. Can you imagine winning an Academy Award for maths? So that's one for the scientists. Now this method, as you see, is very, very powerful for creating smooth randomness. Lucky for us, there's a function in Unity that creates Perlin noise values. And because I'm such a nerd, what I've done is run that Perlin noise over a whole bunch of X values and drawn a graph. So you can see what the result will be. I've got them in Excel here, you can see. So I've plugged in an X value, and out of the Perlin noise function, I've then got the height. As you can see, these values, they're not random, they're not all over the place, but you can see that one point follows the next. So these points are going upward trend, and then this one here, now we're going in a downward trend. So they're not, as random would be, up and down jagged like this. So we've created a nice random smoothness, which gives us the profile of a landscape. It looks like a mountain range. Okay, albeit it could have a few tweaks in that, but it's a lot better than pure random. So we use Perl and noise function in our generate landscape code. So let's just open up that code. Now I've already edited this, and you can change your code, but I'll just go through the changes that I've made. So first of all, I've left the width and depth there that we had before. We're now going to add a height scale so that we can actually control how high things get by multiplying them. And then also a detail scale on how detailed our landscape is going to be. What this value does is controls which part of the Perl and noise we're going to use. So if I just switch back to my little graph here, that detail scale will determine on whether we're actually using the points from here to here and we're drawing a landscape like this, or whether we're just using the points from here to here and we're just drawing a small section of this whole Perl and noise string of numbers. So back to Unity and back to my code. You can see that we've got the same loops that we had before, and the Perl and noise itself is in this line. So this is the major change. Perl and noise is under the mathf library, class, method, whatever you want to call it, and it takes in the values of our x from our loop here and the z from this loop here. It then divides it by the detail scale to make these values smaller, because we don't need big values. So in this case, z and x go between 0 and 128. We actually want much smaller values than that. So we divide it by the detail scale. And then whatever value we get out of the noise, Perl and noise function, we're going to multiply the height scale to lift the whole lot up to make it more defined. And in this case, we've set that to 20. And the rest of the code is basically the same. So if we just save that, switch back to Unity and run, you can now see that the landscape has some definition. And you can see those wave-like forms appearing in here. Okay, so let's just find our landscape in the hierarchy. We can modify our landscape using these exposed variables. Let's change the detail scale and let's ramp that up to, say, 50. And then run it again. Now you can see we've got less waves in this landscape. Okay, so we've actually narrowed our numbers, our Perl and noise numbers, down into a smaller range. It's still spread out over the whole thing, but it's much smaller. And if we do increase that detail scale up to, say, 100 and then run it, you can see that we're only getting quite a small section. Okay, so with a high detail, if I just switch back to Excel again, with the high detail, we might only be getting this bit here spread out over our whole landscape. Whereas with the lower detail, leaving the X values quite wide, X and Z, you might get this part of the landscape. Switching back to Unity, if we went to a detail scale of, say, 5 and run that, you can see it looks at random initially, but if you have a good look at it, you'll see that it's all of those waves. It's not actually random. The height doesn't do any justice to this. If I just actually bring that height scale down by half and then run that again with the bigger detail, we're getting much more of the Perl and noise. If I zoom in you can see the waves, all the ups and downs. They're still there. The blocks are still influenced by the previous block. It's not purely random. It's also not particularly pretty like that either. But it depends on what you're trying to achieve with the purl and noise. Okay, so I'll set my values back to what they were before, which was 20 and 20. Let's just run that again. Okay, that's quite a nice looking landscape. The next step in creating a Minecraft looking landscape is to add some different blocks with different textures on them. So let's add in a sand block. So we make another cube and we will grab hold of a sand texture that I downloaded. So here's a sand texture, bring that in and drop that onto our block. So that will create a sand block. We want to make that into a prefab. So we grab our cube from the hierarchy and drag it into the project. And that will give us this new cube. We're going to call that sand prefab. Okay, you can then delete the sand prefab from here and then create another cube and we'll make that snow. So I've got a snow texture as well. I'll just bring that into Unity, add that to the block, make it into a prefab, call it snow prefab. Okay, and delete that from there. Right, so we want to open our generate landscape code again because we're now going to change it so that there's 3 different types of blocks. We've got our grass block. We're going to create a sand block. And we're going to create a snow block. Save that. Switch back to Unity. On the hierarchy, select the landscape and you'll see the exposed sand block and snow blocks have come up. So you can grab your prefab, snow prefab, put that there, and the sand prefab and put that in there. Okay, so let's go back to our code and use these blocks. So the block gets instantiated on this line here. We're going to set which block gets instantiated based on the value of y. So let's use an if statement. If y is, say, greater than, I'm not sure what the height of these blocks being generated are at the moment, so we'll just, with a bit of trial and error, try this out. I don't think it looked like it was higher than 20. Let's try if the height is greater than 15. We're going to instantiate a snow block. Otherwise, if the height is greater than, let's say 5, then we will do our grass block. And last but not least, if our height is below that, we're going to instantiate the sand block. Alright, so sand we should get up until 5, at which point it will switch to grass until it reaches 15. Then over 15 it will be snow. Let's save that and run our project. Oh, that's not too bad. Okay, so we've got some nice sandy areas where we could put some water. We have snow caps on the top and grass in the middle. So you could adjust that quite easily by changing those if values for yourself. Nice. Now you may have noticed that each time you run this, you get exactly the same landscape. That's because the purl and noise function is getting values starting at the same point each time, because The random noise function is a whole string of these wave-based values. So if you always start in the same space, then you're going to end up traversing over exactly the same landscape every time. So we need to what's called seed the function so that we can force it to start at a different point. So to do that, open your code again, and we're going to add in a seed value right up here at the beginning, and we're going to base that seed value on the network time. The network time value is of double, so we need to make sure that that's set back to an int. And we're going to multiply this by 10 as well, because it gives you decimal places, and you just want to lift that up a bit further to get a better seed value. Okay, so there's our seed value. The seed needs to be added onto the x and the z. And so we add the seed just in here, and make sure that you put brackets around it so that you add the seed to the x and the z before you start to change its value, or to scale it like that. Okay, so we'll just save that. When you run that now, you'll get a different landscape each time. So here's one landscape. Okay, we've got two white peaks just here. Just take notice of those, and we stop running and run it again. Okay, and you can see that it's changed. So you can modify this by changing your detail scale and also the height if you want to have different effects in the environment. All right, now let's add a first person into our scene so we can actually walk around and have a look at the landscape. We're going to do this using an asset that comes with Unity. So we go to Assets from the main menu, Import Package, and go down to Characters. We'll select that package and import it. Now, after it's imported, it will create a standard asset folder, which is going to have a first-person character controller in it. And we can just dump that character into our scene, and it will sort of take care of all of the navigation and key controls for us, rather than us having to do it all from scratch. This character also has physics on it so that it will run into the blocks, and then you can jump up using the space bar. Right, so that's imported. Let's find it in Standard Assets, Characters, First Person Controller, Prefabs. There's two in here. There's an FPS controller and a rigid body FPS. We're just going to use the normal FPS controller. Just drag that one into your scene like that. Now, we don't have a landscape to put it on because it gets procedurally generated, but we just need to make sure that when it is created, it's somewhere over the landscape. So just having a look where this guy is positioned, it's at -12 in the X and 23 in the Z. Now, we know from our code that the X value of the landscape extends between 0 and 128, and so does the Z. So at -12, this character controller is going to fall off of the world because it won't be even over it. So I'm just going to change these values to 50 in the X and 50 in the Z to ensure that that character controller is over the landscape. Now, 80 is probably a bit generous for the landscape. It's not up that high. I might just set it to 50. See how we go at 50, 50, 50. Now, if we run that, okay, we've now got our character controller that we can then not move around in here just yet. We've got these errors coming up because there's two audio listeners in the scene. The reason for that is the old camera is still there. So we need to delete that camera so that the camera on the FPS controller is in charge. Okay, let's run that. Okay. And it's now working with a mouse look built in and the sound for the footsteps. The physics is working. You will run into the blocks, and you can use the space bar to jump, and that will jump up a level. So you don't need to make any extra setting changes in order for that to work. Okay, so that's your first person controller. By now, I guess you're ready to start destroying some of the blocks and go mining. Before we can do that, we should add a crosshair to our screen so that we can aim it at a block and then destroy that block, because the mouse is under the control of the FPS controller and it moves around on the screen, but not necessarily where you want to destroy a block from. So to create the crosshairs in the middle of the game, I've just found a crosshair PNG file that I'll drag into my scene. Just put that in the root of the assets directory. There it is there. Now this image needs to be made into a sprite before we can use it in the user interface. So with that image selected, go to the inspector and change the texture type to Sprite 2D. Then hit apply, and that's all you need to do to make this into an UI object. Now to put it on the screen, we're going to right click in the hierarchy and pick UI and image. Now that will automatically plonk an image, which is empty, into the very center of the screen canvas. We can grab hold of the crosshair sprite and set that to the image's source image in the inspector, and you'll see that you get your crosshairs come up in the screen. And if we just run that, as we move the mouse around to look, it will also move the cursor. The cursor will stay smack bang in the middle of the screen. The reason being is that it's automatically, by default, anchored to that position. If your image isn't anchored to that position, select it, and in the inspector you'll find this little rect transform box up in the top corner here. If you click on that, you can set the pivot point for an object, and if you hold down the Alt key, you can also set its actual position. So if you want it up in the top left, top left corner, you would click on this one, or you can move it over to there. We want it in the center, so we're going to put it right there, and we're also going to anchor it there as well. To program for a mouse click and the cursor being over a block to make it disappear, we're going to go back to our generate landscape code, and we're going to add in an update function. So you'll have an empty update function in your code, and this is the code that you need to add in at this point. So what it's doing is testing if the mouse button is down, the left mouse button, which is mouse button 0. This code will also detect a touch on the screen on a mobile device. So it's sort of multifunctional in that way. We're then going to shoot a ray from the center of the screen out into the world. A ray is like an invisible straight line, like a laser light going out into the world. And we create that ray, which is here, using the camera.main screen point to ray function, and we give it the center of the screen. The center of the screen is going to be half the width, half the height in the X and the Y, and it's going to be at 0 in the Z. 0 in the Z is the camera. So the camera sits at 0 on the Z axis. You can move that around, but for now it's just from 0, right from the center. And we cast that out using this physics raycast function. So we give it the ray and we send it out into the environment for a distance of 1,000 units here. And whatever it hits gets stored in this hit value. If something is hit, we can then use the hit.transform.game object to destroy what has been hit. Now, in Minecraft, you have to be a certain distance from blocks in order to destroy them. You don't have sort of like an endless range. You can destroy something on the other side of the mountain. You've got to be within, 5 blocks or something to destroy things. So you can change this value here if you want to be closer in your game to destroy a block, and you could just reduce this down to 50 maybe. You just have to play around with it. If you run this code and you're not destroying a block, then this value is too small. You need to ramp this up and make that ray longer into the environment. Right, so once you've typed that in, save it and go back to your world and press play. And once your controller hits the ground, you should be able to put your crosshairs on a block, and when you click the mouse button, it will destroy that block nice and conveniently for you. Like that. Now, as you can see, I'm clearing a hole in our world, and there's nothing inside it. We haven't created these blocks. We could, at the time of generating the map, create all of the guts of this map, all of these blocks inside here, but the lag on the game would be tremendously awful, even if you turned on occlusion culling with the blocks. And believe me, I've tried this. It's still really, really laggy, and I managed to crash Unity several times doing it that way. So we're not going to do it that way. So how about we do something where we click on a block and destroy it, but when it gets destroyed, it creates the blocks around it that need to fill in that gap. Okay, so let's stop playing and start looking at the logic behind that. Before we start overhauling the code to take care of all of the blocks that are underneath the ground, first of all, we just need to clean up some of the code that we've already written. Now, if you go back into Generate Landscapes, inside of these nested for loops, there was a whole bunch of code which is now being replaced with create block. So what I did was to remove these lines. These were up here. They're now in their own function because we're going to need this function and call it a few other times from different places. So it makes sense to put it in here. So create your own function called create block. You want to put it outside of the start function. So this is the starting bracket of the start function. This is the ending bracket of the start function. Create block after all of that. Move the code that was up here down into here, and then put this line where these other lines were before. Save it and run it just to make sure that it's still working. It will work exactly the way that it did before. It's just now using this create block function instead. Right, we're ready to restructure our program to include blocks that are under the ground. Now, we already know we can't draw them all at the same time, otherwise it's just going to be too laggy, and that will really affect gameplay. We need to create our world in its entirety, but we need to do that in memory, not by creating the blocks in the game view. So we create a 3x3 matrix that's going to store all of the values of the block. So just to illustrate what I'm going to do is I've got this diagram here of a three-dimensional array. Imagine that your game world in Minecraft looks like this. Okay, each block can exist in one of these little cubes, and Minecraft has a lot more than a 3x3 here, but this is just to illustrate. So if we create an array that will store all of these values, we can index the array based on the position of the block. So the block that's at position X equals 0, Y equals 0, Z equals 0 could be this block down here. And so we can reference that in code. This becomes 0, 0, 0 for this block. This block up here is going to be, let's say it's 0 in the X, and it's 1 in the Y, and 0 in the Z. And then this block here becomes 0, 2, 0. That would make this block, let's say that this is the Z direction in this case, This block here would be 0, 0, 1. And then this block here is going to be 0, 1, 1, etc. So that whole block, the whole array, is going to have all of these indexes into it based on the block's position. So we can easily get values out of our array and put the blocks into the world, and then when the blocks get taken out of the world by clicking on them, then we can take the values out of the array. So we're keeping track of the world on two planes, one in the scene as 3D blocks and one in memory as this three-dimensional array. Firstly, in order to get this to work, each block needs to be defined as its own class, so that you can keep track of the type of block that it is, whether it's snow, grass, or sand in this case, and whether it's visible or not. We want to keep track of whether it's visible or not, because if it's already visible, we don't want to instantiate another block over the top of it. Therefore, we can go, if visible, don't bother. If you're not visible and you need to be visible, then we do want to turn you on or instantiate a block in that actual position. So at the top of your code, outside of your generate landscape, just above it, you want to create this public class for block with a integer type of type and a Boolean value for vis, which is going to be set through this constructor here that we'll use in a moment. So that's what each of the blocks will consist of. Right, going down in the code, we now have to create our three-dimensional matrix to hold all of these blocks, and it's going to be an X, Y, and Z values for the size of the matrix. So we have the X is the width, the total X, the total Z is your depth, and your total Y is going to be your height. In this case, we've made them 128. And notice that in order to use these values to declare that array, we have to make them statics. Okay, so they're the new variables. Now we've got to create the actual matrix or our three-dimensional array, and we do it like this in this piece of odd-looking code. So each part of the array is made up of a single block, and to declare the array as three-dimensional, it's square brackets with 2 commas in the middle like this. Then it's the name of the array, and then we create the new array with new block, and then width, height, and depth, which gives us our X, Y, and Z dimensions of that array. So that essentially gives us, if we just switch back to that other drawing, it gives us this, but 128 blocks in all 3 directions. Okay, right, so we've got our array. Now we need to put some values in it. So the next change we've got is this here, and I'll come back to that in just a second. Firstly, you'll notice that the create block function has changed. It has this true on the end. And if you look down to the function, you can see that this new variable is a Boolean value, and it's called create. When we create the top layer of blocks, we want them to be visible. And by setting true here, it creates that top layer of blocks. And the true comes through down into our code, which says if we're creating a block and its create is true, then instantiate the block. We can also create blocks with false in here, which will create a block in our array, but it won't actually draw a block in the scene. Now the world blocks array is then set using the X, Y, and Z position of the block, because the X, Y, and Z position is the actual integer position of the indices of the array based on the position. We use this same method if you've gone through the Bejeweled tutorial as well for positioning items, because each block is 1 by 1 by 1. So as you move it around in the scene, at a distance of 1, we're incrementing each position by 1, which is the same as indices in the array. So the physical world is replicating the memory or the virtual world. Now, in each position of the array, we create a new block. And in this first instance was our snow blocks. So the first block is created with a type of 1, and we send it create, which sets our visible value to true for this initial top layer of blocks. So they all have visible of true, which we will use later on. Okay, now if we just go back up to our start function, you'll see that there is this little while loop under our create block. And what it's doing is it's starting just below y minus 1, below the block, the top layer of blocks. So it's going down to the next one, and then it's creating a block in that position. But it's creating the block with false, so it won't get drawn. It will just get created in memory with a type of snow, grass, etc. And this loop keeps looping, so it keeps going down through the layers. So if we go back to our little diagram, what that's doing is that this block here will get created and drawn, so it's on the top, so it'll be grass or whatever. And then that while loop starts going down, straight down, and creating all of these blocks until it hits 0, which is the bedrock layer. It won't instantiate a block or draw it, it just creates it in that array, so it does exist virtually, for want of another word. Okay, so that's what's happening in this while loop. So for each block on the surface that is created, this while loop goes down, 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 digs right down to the bottom and creates all the blocks that are going to exist underneath it. Okay, so moving along, I'll come back to this draw block function in a moment because it's new, but if we go down to update, you'll see where some big changes have taken place. We still have our mouse down, we still have our hit, and we've got our ray cast, etc. Now we're adding this line here. So if y is 0, then we're going to return. We're going to quit out of this function, because if y is 0, we don't want to remove that block. It's the bottom block. It's the bedrock layer. We haven't actually set it to be a black block or anything in particular, but you could do that. You could do that up in create blocks here. You could have another layer down here. If y was equal to 0, then you could create a black block or something. You can add as many different blocks for different heights as you like in this part of the code. Okay, so if we go back down to here, okay, so if we're not at the bottom layer, that we're trying to delete some other block, then it will grab the position in the array of where that block exists and set it to null. So it would actually remove it out of the array altogether. And it does that just before it deletes the object in the scene. Okay, so it's removed from the scene. It's also removed from its parallel array. Okay, then what we have to do after we've removed a block is look around that block. Look at all the spaces around that block and have to fill them in, so that when you delete a block, you want there to be ground underneath it, or you want there to be a wall behind it. You don't want to be able to see through the map at all. So if we just go back to our drawing again for illustrative purposes, let's say that this block is getting clicked on and removed. It gets removed. And that means that if we were standing here looking this way, we see this block, which is like this, crudely drawing it. So we delete this block. This block hasn't been instantiated into the world yet. It's in the matrix as something that has to be drawn, but it won't get drawn until we delete this. So if we delete this, this block here needs to come into existence. Now, if we were standing here, which means that this cube's also existing, this one might not have been drawn. So when this one's gone, we'll be able to see that there's a space in there, so we need to draw that one as well. And we may need to draw that one. And we may need to draw the one that is sitting on top of here. And all of the other ones that are around this particular block will need to be drawn. We've got the X, Y, and Z positions of this block, so we can easily calculate what these X, Y positions are for these surrounding blocks. Because if this one was 0, 0, 0, then this one here would be 0, 0, negative 1, because we're going backwards in the Z direction, which is what we talked about previously. So each of these blocks around here are plus or minus 1 on the X, Y, and Z indices or dimensions of this array. Now, the long way to do that is to write out each one with a little formula, taking 1 from X, none from Y, none from Z, and then 1 from X, 1 from Y, none from Z, and counting through all the different possibilities to get all of these different combinations of the indices of this block, which will make more sense if you do that the long way by hand. But I find it easier if you use a for loop. It's a lot less lines of code, and I've created a 3-nested for loop here, which takes X, Y, and Z from -1 to 1 for all of them, and loops through and just keeps taking those off of the current block position, which essentially covers all of the surrounding blocks. So eventually you'll have got to all of the surrounding blocks. And then for each one, it calls this draw block function. So draw block and give it the neighbor's coordinates. What does the draw block function look like? I've added that in here just before update, and you can see that the first part is testing if the block exists. So if the block at that position exists, which means we're not trying to create a block outside of the array. So if we're trying to grab part of the array that doesn't exist, so let's say you've clicked somewhere and it wants to create block 129, which won't exist because our matrices only goes up to 128, then we want to return from this function. We don't want to draw a block in that area. Next, we ask if the block we're about to draw is visible, or in this case, if it's not visible. If it's not visible, we go ahead and draw it. If not, then we just want to skip over all of this code and forget about it because it already exists. It's already a game object. Right, so if it's not visible, we then set it to be visible, go through all of the types. Whatever type that block is, we then draw, whether it's a snow, grass, or sand block. If it's not one of these types of blocks, it's somehow ended up with a value in it that we didn't create, or the block is empty. So it could be 0, for example, if it's empty, in which case it shouldn't be visible in the array, and therefore we just go and turn it off again. All right, so that is the code for generate landscape. I'll just scroll through this slowly for you now if you want to pause the screen and check that your code is the same. It's very important. So there's the generate landscape start of the class. Here's the start function. Make sure you've got all your brackets. Here's the create block function. Okay, that's the starting bracket, that's the ending bracket. Here's the draw block function. And then we have our update function, starting bracket, ending bracket, and this is the last bracket for that entire generate landscape class. Okay, so if we save that and flip back to Unity and run it, wait till we fall to the ground, we should be able to dig a hole and we won't dig through to the other side anymore. Because every time we delete a block, our function zips around and tests whether it should draw other blocks around it. And you can see the blocks are still in different colors based on the height. And we can dig down. We've got a long reach on this one to there. So it won't go any further than the bottom layer. Now, at the moment, I can't fall down that hole. And you do fall down that hole when you're playing Minecraft because your character's a lot slimmer than this one. So I'll just show you quickly before I end this tutorial how to make your character a little slimmer. We're looking for the collider that's on our FPS controller. So if you click on FPS control in the hierarchy, put the mouse over the scene and press F, which will focus on your character. You can see the collider here as a capsule collider in green. We want to make him a bit slimmer. So over in the inspector, we need to find the collider's radius, which is here in the character controller and radius. And we can just make him a little slimmer, just like that. Okay, 0.29 I've got it at. Let's see if that's narrow enough to fall down a hole. The best way to test this is probably to dig straight into a mountainside and see if I can walk into it. Yep, it seems to work well. And then if I dig a deep hole, I should be able to fall down. Yep, okay, that's great. And then we should be able to dig our way out, which I'm probably not going to attempt now because it'll take me forever. Yeah, but you can't jump up just like in Minecraft if something's above you. It'll take me forever to get out to freedom. Oh, there we go. There's the sky. Okay, so that's the end of this tutorial, which is almost an hour long. Thanks for sticking with me. It's no trivial matter, obviously, to create something like Minecraft. There's a lot of tips and tricks, and this covers barely any of it. It's just one little part of the landscape. Even Notch himself says that he does use Pearl and Noise as the basis for the landscape, but they use a lot of other tweaks as well within there to make it more realistic. And of course, we would still need to add a fair bit to put trees, to put minerals under the ground and that type of thing. So we'll start looking at digging out caves and putting some different objects on top of our terrain in the next tutorial for the Minecraft one. Thanks for listening.